In this video, we're going to take a first look at the new Revopoint Inspire 3D scanner. We're going to talk about the specs of the scanner. We're going to walk through how to use it and where it fits in their 3D scanner lineup. Keep in mind this is part of a Kickstarter campaign that'll be starting on August 16th, 2023. But if you want to learn more about this scanner and how it works, stay tuned. Hey everyone, this is Matt with Learn Everything About Design, and in this video we're going to be going over the Revopoint Inspire 3D scanner. A little while back, Revopoint reached out to me and asked if I'd be interested in doing a video with this new scanner. So full disclosure, they did send me the scanner for free, so you can consider this a paid advertisement for them. Now, with that in mind, I have used the scanner, I've been playing around with it, and these are going to be my own opinions. I don't have a script to follow, and I'm going to give you as much information as I can, including where the scanner sort of fits in the scale of the Revopoint lineup, and whether or not you can use it for the types of things we cover on this channel. So the first thing that we're going to do is we're going to talk about the Revopoint Inspire scanner, how it compares to the Revopoint Mini and the Pop3, and where we think that'll fit into the overall scheme of these DIY or hobby or entry-level scanners. Now, keep in mind, there is no pricing available on this scanner just yet. Now, if you're watching this video, you're likely watching it the same day the Kickstarter campaign has launched, so you probably know what the price is. I'm going to take my best guess to figure out where this fits in the lineup, but keep in mind that pricing will be released when the Kickstarter campaign is set. Now, with that in mind, I do know that there will be some discounts for the early bird adopters. So if you are looking to get yourself into 3D scanning and you want to do it on the cheap, make sure that you check out this Kickstarter campaign as well as some of the other scanners that Revopoint has to offer. With that said, let's talk about the three main scanners in the Revopoint lineup. We have the Revopoint Mini, the Pop3, and this new Inspire. And when we look at the specs for these, there are going to be some variations or some differences here. Keep in mind, I am not talking about the Revopoint range, which is intended to scan larger objects. That's something I will likely get into in future videos. But the Mini has a single frame precision of 0.02 millimeters and a distance between points of 0.05 millimeters. When we go to the Pop3, we're looking at a single frame accuracy of 0.1 millimeters and a single frame point distance of 0.05 millimeters. Now keep in mind, I'm talking about the difference between single frame precision on the Mini and single frame accuracy. The accuracy numbers are generally going to be larger than the precision numbers, but not all scanners have the same numbers that are published, so we have to use what we have in mind. And when we're talking about these scanners, the Mini is intended to scan small objects, where the Pop3 is looking at sort of medium objects. The Inspire comes in a little bit lower than that, with the single frame accuracy at 0.2 millimeters and the distance between points at 0.3 millimeters. So if we were just to look at these three scanners on a spec sheet and the pricing between them, I would assume the Inspire scanner is going to be coming in underneath the price point of the Pop3. Now, when we think about using these sort of DIY or entry-level scanners, one of the main benefits, other than the price for the entry, is the fact that you don't need the hardware to support these. When we look at higher end, whether we're talking about prosumer or higher end scanners that are intended for high accuracy and high detail scans, oftentimes the big cost associated with those, other than the initial price of the scanner, is going to be the computer resources that are needed to support those. The Pop3, the Mini, and the Inspire can all run from your cell phone. So if you have an Android or an iOS system phone, you can get some accessories and you can take a look at scanning on the fly. And then you really don't need that much in terms of a laptop or a desktop to process these scans. So that's a big benefit. When you're talking about the cost of entry, you can spend $300 to $500 getting a scanner and run these things on a pretty minimal laptop. When you get into higher end scanners, then you're talking about spending thousands of dollars on the computers, the laptops to support even scanning with that. And then you have this software that goes along with it. So now that we've gotten that out of the way, let's talk a little bit about what you get when you buy one of these scanners. Just like with pretty much every scanner nowadays, you're going to get a handful of things. The scanner itself, you're going to get a tripod that comes with it. This one comes with a very small turntable. It does have a couple of mats. One of the mats they call the magic mat, I believe, which is basically a fabric mat that you lay down that has randomly spaced marker dots on it. And there is a sampling of markers that go in there as well. They do also have a mobile kit available, which comes with sort of a handheld battery that you can screw into the bottom of the scanner. And it also has a cell phone mount as well. So it really helps if you're trying to scan on the fly and you don't want to carry a laptop around with you. You can do everything to your phone, and then you can transfer that from your phone directly to the RevoScan software. With all that out of the way, now let's talk about actually using the 3D scanner. Now the RevoScan software is free to use, and for the Revopoint Inspire scanner, you need to have at least 5.2 or above on the RevoScan. I'm currently using 5.2.3, and I've noticed that with the release of this Inspire scanner, they keep making changes and additions to the RevoScan software, so make sure that you do pay attention to the most current version, as it might open up some new options for you. Now, once we have RevoScan launched, I'm going to begin a new project. Now, once we have a new project, the settings that we have available to us are going to be somewhat dependent on what we're trying to scan. Now, if you've taken a look at some of the other scan videos I've done on this channel, you will have seen this KTM bar clamp that we've scanned before. Now, this has a gray spray paint primer on it, so it's a good candidate for scanning. We can get some good detail off of it, and it's not really a sort of a scan prep spray, but it's the next best thing. If you're talking about parts that have a primered finish on it, this is going to be much better than a shiny black or a shiny aluminum finish. So with this part in mind, I have it sitting on this round mat that has markers on it, and underneath that, there is the small turntable that does come with this. Now with that turntable, it is not keyed into the software. So essentially, as soon as we apply power to it, it's going to begin spinning. So keep that in mind. The way that I've been using this is I've been plugging it into the USB port when I need to turn it on, because it's a little difficult to get underneath this mat, which is larger than the size of the turntable, and adjust the dial or flip the switch to turn it on and off. So that's the way I've been using it, and I have been using this sort of alignment mat. If you leave it here for too long, it starts to sag because, again, it is a little bit bigger. So if this is going to be a more permanent solution, I would suggest getting a sort of a flat piece to go underneath this, making sure that it's black. With that said, in terms of the setup, the scanner is fixed. It is on a tripod right now. And on the left side, we've got a couple of settings here. We've got auto exposure for the depth camera. We've got auto exposure for the RGB camera. And then we've got white LEDs. Now, in the case of scanning something like this is a mechanical part. The intention would be to reverse engineer it. I would turn the white LEDs off. Those are really in place to help us when we're doing color captures, when we're trying to capture information, which we'll talk about a little bit later in this video. I have another scan that I'm going to show. So I'm going to toggle off color scanning as well. We don't need that color scanning information. When we are doing color scanning, each of those points is going to carry that color data with it. And as we go through the process of fusing the point cloud and moving into the mesh, that color data will be carried along with it. For a part like this, all we really care about is the mesh itself. So as we're looking at these settings, auto exposure is a nice setting, but if you take a look at the depth camera, you can see that we have a lot of this red area that's displayed on the part. It might be better for us to manually reduce that until we just have a little bit of that red, making sure that we're talking about the exposure limits. We don't want to overexpose this, because what ends up happening is it makes it difficult for us to capture accurate data. With that also said, keep in mind that you want to play around with these settings. Sometimes it might make the most sense to manually adjust that exposure. In other cases, toggling on auto exposure could give you a better result. You won't really know until you try. With the auto exposure, do note that we are seeing a lot of extra noise at the bottom of the part. When we toggle off auto exposure and we bring this down to say a 6 or a 7, that gets a little bit better. So for this initial scan, what we're going to do is we're going to toggle off the auto exposure for the depth. The RGB we're going to leave set to auto. Again, we're not looking at capturing color data, but we're just going to leave those settings as auto for now. On the right-hand side, we do have a handful of important settings under scan settings. When we use these scan settings, we have two options, a standard accuracy and a high speed accuracy. When we do high speed or standard, we're essentially going to be getting the same quality of scan, but when we move to high speed, we actually drop the ability to use marker tracking. So for something like this, where we're on a turntable, we're looking at a stationary scan, the standard accuracy will open up the ability for us to use marker tracking. And that's the whole intent here, for us to use the markers that we have available. So standard accuracy, marker tracking, this is a general object. When you move into using things like feature tracking, you'll get options for things like dark objects or faces. But keep in mind that when we're using marker tracking, general object is the only thing that we have. Next, we have this option called hide surfaces. Now, in this case, and in most cases, if you're scanning objects like this, it's likely going to be on a desk or on a table. Now, you can kind of see in the bottom left-hand corner for the RGB camera, it is sitting on a desk. And if we toggle on this hide surfaces, it will be able to find those planes as we're scanning, and it'll be able to remove them and not capture that data. So that's a great option to turn on, especially if you're working in a scenario like this. What you'll find if you're using a turntable and you do have a stationary desk underneath it, a lot of times you're going to get a lot of noise from those surrounding objects, if it's the desk or something that's sort of near the scan object, and you're going to end up having a lot of problems. Another thing that we should note is, as I've been playing around with these settings, the auto exposure setting over here has changed automatically. So always double check your settings, play around with them. And again, if you want to play around toggling on and off the auto exposures, you can always do that. I'm going to go ahead and leave it on auto exposure just to make sure that it doesn't drop back down. And I want to talk about one more thing before we get started scanning. We have a scanning distance option here. And what this is really talking about is automatic clipping of scans relative to where we are in relation to our scan object. Now, the camera that we see as we move the object around, or if we move the tripod around, what's going to end up happening is anything that's closer than 180 millimeters or farther than 600, that's going to get automatically clipped out of the scan. So again, another great option if you're using a stationary scan like this, where you know things aren't moving around drastically. If you are doing it with a handheld scan, I would suggest stretching that distance out a little bit more, and that way you're not worried about clipping any critical data. So with all that, now it's time for us to start our first scan. We're going to get started by clicking Start. Then I'm going to plug in the turntable and allow it to just begin rotating around. Notice here that it's telling us that tracking is lost. If this happens, you want to make sure that you do stop the turntable. And if you have to, you can reverse it or you can reposition the scanner. And one thing that you'll find is when you're scanning smaller objects like this, you may want to move the scanner a little bit closer. Anytime we're seeing green on the screen, this means that we're capturing data. Anytime that it's red, it means it's not able to capture and save those points. So once we move things around, make sure that we're capturing the data again. We're getting a green preview. We can go ahead and plug the turntable back in. This looks extremely messy, but what we're really focused on here is that the object that we're trying to scan is green. I'm going to go ahead and unplug the turntable. I'm going to pause the scan and just take a quick look. And I just want to make sure that I have enough information for the base part. And I'm not worried about all the extra noise right now. I just want to make sure that the base part is okay. And once I'm happy with that, I'm going to go ahead and say okay. What we want to do before we begin processing anything else is I'm going to create a new scan. Now for the new scan, I'm going to scan the bottom of the object. So I'm going to go ahead and flip it over. This time the scanner is a little bit closer. Once I'm happy with the orientation, I'm going to click Start, allow it to start capturing, and then plug in the turntable. Once again, it is important that we think about the orientation of the scanner, the turntable, make sure that we have good visibility, good lighting, and that we're not getting into a situation where the markers are becoming obscured. We want at least 4 markers visible at all times, and that'll help us track the object as it's rotating around. I have the turntable set to go relatively slow, which means that each frame that we're capturing, there's likely going to be overlapping data. That's okay, we're going to clean that up a little bit. I just want to make sure that the base object has enough in terms of the mesh points or the point cloud in order to capture that data. So once I'm happy with it, it's rotated around, I'm going to go ahead and unplug the turntable, pause, just rotate, make sure that it does look pretty good. And that looks pretty good. And then we'll complete. Right now, things seem a bit messy, but the first thing that we're going to do is we are going to take a look at using Fusion. Now I'm going to go back to the first scan for this. Now the first step of this is to take our raw scan data and to use the Fusion option. Note that there is a one-click edit option here. I'm not going to be going through the one-click edit because I want to talk about each step of the process. When we select Fusion, what we're doing is we're taking all the points that we've gathered and we're merging points based on some initial settings. Now there are 2 options here. There's an advanced option and a standard option. The advanced option, in the case of the Inspire, will let you go down to 0.2 millimeters for the point distance. The standard option will allow you to go down to 0.1. Now, if you think back to when I mentioned the specs of the scanner, I said that the point distance was 0.3 millimeters. So how are we getting 0.1 millimeters between each of these points when we weren't able to capture that from a scan? Well, keep in mind that those point distances are based on a single frame. We captured over 200 frames as we were rotating this part around. So each time the scan rotated, and we've got a total of 571, each time it rotated the part, we captured more data. So even though the points were 0.3 millimeters apart, that doesn't mean that the captured points are at those distances. So we're going to use the 0.1 millimeter distance to try to get it as close as possible. And this is going to fuse any of those points together that are within that range. Now, when we think about processing scans, the general rule is to have the scan data as raw as possible, at least have that saved, because as soon as we begin processing it, as we begin removing points, as we begin smoothing things out, we begin to dilute the data. Now, I should mention that the Inspire as well as the Pop, these are not scanners that are meant for detailed reverse engineering of small parts. This part is small compared to what we should be scanning with it. So just keep that in mind. This is a little bit outside of the range of what the scanner is really intended for. So far that looks okay. The points are fused, and now I'm going to move to isolation. With isolation, what we're looking for are points that are outside of the range of the main capture of the scan, the main body. So we're going to use the default 36%. We'll select detect. And what this should allow us to do is detect points that are outside of that sort of central mass that we scanned. This will help us get rid of any of the noise that we captured from the turntable, from the desk that was accidentally brought in. We simply hit apply and all of that will be removed. The next thing that we need to do is cut away some of this noise at the bottom. Now, this scan orientation was meant to capture the top and the sides and underneath these areas, but this bottom section where it was sitting on the turntable, that's not really important to me because it's captured in the other model. So what I can do is make sure that I have the select through option. I'm going to go to my polygon selection and I'm just going to cut straight through here and just get rid of that entire bottom. Once that's all selected, I'm going to hit delete on the keyboard and just get rid of it. You'll notice there is a little bit more kind of floating in the air here. So we're going to rotate around. This time I'll use the lasso and sort of just draw around those areas. Hit delete to get rid of it. That looks pretty good. And we do have a little bit of noise up here. I'm going to be okay with some of that, but I'm going to get as close as possible to removing that. I'm going to again use the lasso tool and get rid of some of that and just hit delete. So that looks okay. I'm happy with that result. And before I do anything else, I'm going to go to the second scan and do the same thing. So we're going to go to Fusion, Standard, all the way down to 0.1. We'll apply that. Once again, it's looking at all the raw data that we've captured. For the second scan, we only captured 384 frames instead of the 571 for the first scan. Still plenty of data. We should have good usable data here, but I can't stress enough, this is outside of the intention of the scanner. The scanner is meant for medium-sized objects, not small, precise reverse engineering parts. But knowing what we do on this channel and knowing the questions I get asked, we need to make sure that we can figure out if this thing actually works for what we're trying to do. So once we've fused all those together, next step, I'm going to go to isolation, detect. Hopefully it'll be able to gather information outside of the main core of the scan. And what this is looking at, the isolation rate is based on the number of points. So it is able to capture and select all the stuff out here. We'll apply, which will get rid of it. And then once again, all this noise here, we're going to rotate it around because that is not really important for what we're doing. We're going to use our selection tools, and we're just going to cut through here and get rid of as much of that as we can and hit delete. There is a little bit more kind of hanging out here. Once again, I'll grab the lasso and go around, delete that, and then we'll check over here. Looks like we got some points floating out in space. Once we have these disconnected, you can also go back and use the isolation detection again. A lot of times reusing the tool after we've removed some of the points, it'll be able to grab those and we can delete them without having to do the manual selection. So that looks pretty good. Now I will say that we weren't able to capture a nice crisp corner. So this is a sharp machined edge and it's a little flat, a little rounded, but once again, outside of the area where the scanner is really intended to work. So we're gonna play around with these two scans. But the next step for me is to take a look at overlap. Now, overlap is important because we created, in this case, 300 to 600 scans. And every time the part rotated, it captured more points. So we're going to have a lot of points that are overlapping, even though we use the turntable setting. We're going to hit apply and remove those. And we'll do the same thing for the original scan. We're going to go to overlap, detect, again using that default 0.25 millimeter setting, and apply. And notice so far, we haven't done any decimation. We haven't smoothed or simplified the point clouds at all. We've only taken the overlap or the isolated points and we've removed those. Now that we're at this stage, the next stage for me is to merge those two point clouds together. So I'm going to go to merge, select both, and we have two options here. Feature will try to automatically put them together, and marker will allow us to make manual selections. I'm going to say okay and see if the feature alignment can do it for us. Ideally, this works, and it works pretty well. But in some cases, especially if we've done a lot of pre-processing to the points, we might find that it's just not giving us a good result. So let's take a look. Obviously, that is not a good result. So those are not putting those two together. So we're going to go back to the original two, get rid of that third one, and use marker option. So when we use the marker option, I want to rotate them around so they're sort of in the same orientation. And I'm going to put points in the same areas. So we'll do 1, 2, 3. I'm going to rotate around to a flat side, put a point there. Now, if you happen to make a mistake, you can always go back and re-click those points to remove them. And it looks like I've got a couple of extra points here. Let's see if I can find them and remove them. Yeah, okay. So we want to make sure point 1 is over here, point 2 is over here, 3 is there. Then we're going to put 4 on the side. And we've got another flat over here. We'll put 5 over there. And we'll see if that works for the marker alignment. Now there is a chance that this doesn't work. And again, it comes back to how much processing do we do to try to get these two cleaned up a little bit. Now, if I'm not happy with this, I'm going to go back a step. I'm going to hit cancel, and I'm going to go back to the isolation step. I'm going to delete those merged. Go ahead and just select and delete both of those. And I'm going to go back and begin doing a little bit more processing. So I want to smooth this out. When we're talking about smoothing, we have to be careful with the strength and the times values that we use. The more that we smooth something, the further we can get away from the original mesh. So what we're going to do is try it with the most aggressive settings. Times is going to be the number of iterations that it goes through. Smooth is going to be how aggressive, or the strength is going to be how aggressive the smooth removes the noise data. So we're going to apply that. We're going to just kind of take a look and see what the results are. And that doesn't look too bad. We still have crisp corners here, so we haven't really lost a ton of detail. So I'm happy with that. I'm going to go ahead and do the same thing to the other one. We'll go to smooth using the same settings. That's probably not as good, but it's a little bit better than it was. So now that we've done a little bit more processing, we're going to go back and try again to allow it to manually align or automatically align with features. Now you can see that this is a much better result. It actually looks like it's fairly smooth. We do have some problems on the corners. Comes back to a little bit of noise, but if we're trying to reverse engineer this thing, we're going to get the critical details from manual measurements. We're going to know the whole locations and the whole sizes. So really what we're using the scan data for is going to be the general shape. So I think this is a pretty good result. So I'm going to move back and I'm going to go to the mesh step. And when we do the mesh step, we want to make sure that we're using the merged project. So the model in the merge section, merge 01, is going to be the combination of the first and second point cloud scans. Once we have that selected, we can go to mesh. This is where we do need to be a little bit careful. Now, it can be very easy for us to go to this quality setting and just simply say 6.0. And we're going to go ahead and start with 6.0 and take a look, but then we can go back and do a remesh with a different quality. But basically what we have when we're looking at the quality settings is we're going to be generating the mesh model and controlling the density. So if the point clouds that you have are pretty noisy and we have extremely small mesh elements, the mesh density or the mesh is really dense, then what's going to end up happening is all that noise that we have in the point clouds is going to come through in the final mesh. When you have a larger part, let's say that we're scanning a fender of a car, those are pretty big, broad surfaces. We don't really need the quality settings to be very small, and we don't need those mesh elements to be so small. So as we look at this, you can see that the noise in these areas is coming through because of those mesh element sizes. So let's take this back a step and let's go down to about 4.8 and apply. We're going to say okay, because essentially it's taking a step back to the point cloud that was merged, and it's going to rerun that conversion to a mesh. And once we go back to there, what we're going to see is that there's going to be a difference in that final mesh. We're going to see some of that noise disappear. In some cases, you might have extra noise, but this looks like a better result. Now, this is because the mesh element sizes are now bigger, 0.12 millimeters instead of 0.06 or whatever it was. So this is something that is going to be a big consideration, and it's going to determine how well your part looks. Some other things that we can think about, the sharp corners or the noise that we're seeing on these edges. When we have multiple scans that are merged together, those multiple scans oftentimes will end up having areas where there's noise at the edge of that scan data, a noise at the edge of those captures. And it makes more sense to cut those away and only use a small amount of overlap between the two scans. So you are going to have to deal with that whenever you're talking about capturing multiple scans of a part. We can see the edge where we cut at the bottom of that first scan, and that's okay. Again, when we're reverse engineering, we're going to be using calipers to measure critical dimensions. Now that we have the mesh created, we can use additional smoothing if we wish. Now, if we apply the additional smoothing after the original mesh conversion, we might lose more data. We might lose some additional edges, but it all comes back to thinking about what you need to get out of your scan data. Once again, I can't stress this enough. This is a relatively small part. The distance here for this, it's a bar clamp for one of my dirt bikes. It is 1 1/8 inches across. So we're talking about a part that is about 1.5 inches in a cube. Relatively small, talking in terms of what we're using the scanner for. But I think the results are actually pretty good. I'm kind of surprised at how well we were able to capture this. Could do a little bit better if I spend a bit more time on cleaning up those original scans, getting rid of some of the noise in the corners. But I think for the purposes of this initial video, figuring out how this thing works, I think this is pretty good. The next step for this process is for us to export this. We can export everything. We can export just the point clouds or just the mesh model. We're going to take the mesh model out of here, and I'm going to set this as an OBJ. I'm going to put it into a folder, and I'm going to call this my merge01 mesh, but I want to add a KTM clamp on the end of it, so that way I know exactly what it is. We're going to bring this into Fusion 360, but before we do, I want to take a look at one more scan. I want to talk about scanning something a little bit bigger, something that has color to it. So I'm going to go back to my home screen. I'll save this project. And I want to go back to the a scan that I did previously of a part of the fender of my Mitsubishi Starion. Now, this scan was just the lower portion of the bumper. Recently, we did a video on designing a canard for a car, and we used this section of the bumper. So I wanted to scan this. I had a bunch of markers still on the car, and I wanted to see how the scanner did. Now, the car does have a dent right here. That is very visible, and we can see that the dent has come through. And what we're going to do is we're going to take a look at the raw scan data. We're going to work through this, and after we work through this model, then we're going to work through a color model, and we're going to capture color data, and we're going to talk about that as well. So when we capture this raw data, we have to be careful with the orientation or the angle of the scanner. As we rotate this around, we can kind of see a lot of lines, and these lines are going to come through based on the orientation of the scanner when we're using it. The more that we sit there and capture that same area of a design, the more points are going to begin overlapping. So the first thing that we want to do is we want to fuse this model. I'm going to use the standard option, and I'm going to drop the points down, and I'm going to allow it to go through the process of fusing the points together. Now, once again, we're capturing points at a 0.3 millimeter distance, but that is for a single frame. So as you move the scanner around, or as you just tilt it slightly, you're going to be capturing more points in that area. Using this fusion setting is going to allow us to combine those points together. The next thing that we want to do is we want to talk about smoothing this out. Now, generally, we don't want to smooth out the raw scan data, but again, with a large sort of broad surface, it's not flat, but it's mostly flat. I'm okay with using some aggressive smoothing on the points themselves, because it's going to give me a better quality conversion when we go to the mesh process. So we're going to allow it to do the maximum strength, which is 20, and the maximum number of times to go through, which is 50. So it's going to essentially go through, take a look at all the points. Anywhere that's a little bit low, it'll raise up. Anywhere that's a little bit high, it'll push down, and then it'll repeat that process 50 times. That strength value is going to determine how far it allows those points to move. And then that times, again, is the number of iterations it goes through. Once we have this data, we're going to move on to meshing it. Now, this has already been meshed, but I'm going to go through the process again. And as I mentioned before, the mesh quality is directly related to the mesh element size. So we don't necessarily want to go with a 6.0 quality setting, because that's going to give us tiny mesh elements. And what that means is any imperfections in the scan are going to come through. So reducing that number down, you can see here to 4.5, we still see that dent, but it gives us a relatively smooth scan. We can still see the horizontal lines, again, based on the scanner orientation, but overall that looks pretty good. Next step for me is to go through filling holes. We're going to detect holes using the curved method. And in order to fill these, we have to manually select them. We're going to go through and click on any holes that we want filled. When you're creating the mesh initially, there is an auto hole filling option that you can do based on hole size. But I find that it's a little bit better to do this manually as long as there aren't too many to go through, because there are some instances where I don't want it to try to fill holes. I don't really care about the little gap between the bumper. All I want to do is fill the holes on the area of concern. So that looks pretty good. Now that we've got that, we can also, oh, looks like I missed one. Let's go ahead and detect the holes again. I'll just go ahead and fill that one. And then I'm going to go through the smoothing process. Once again, the number of times and the strength are going to be directly related to what you need to get out of your scan. I think overall we can kind of see where the marker dots were, but overall that looks pretty good. If you want to, you can move on to the simplify process. This will allow us to go through and take those mesh elements and it'll be able to remesh that. In some cases, it'll help get rid of those marker dots. We still see that dent there, unfortunately. But I think this gives us a pretty good result to work with. And it's definitely something that we could use downstream in Fusion to help design our part. I'm going to go ahead and export this as well. I'm going to go ahead and go to the export settings. I want to export this mesh model and make sure that I save it as an OBJ. I'm going to call this my Starian Canard, and we can also take a look at that in Fusion. So the last thing that I do want to take a look at is I want to go back and talk about something that the scanner is probably more intended for, and that's objects that are a little bit larger. They aren't necessarily reverse engineered, but they're going to be parts that you may want to scan for a digital asset or 3D printing or whatever you're trying to do. So what we're going to do is I'm going to get out what's called the magic mat, and then we're going to start a new scan. Now, the magic mat is going to be just a large mat that has a bunch of marker dots on it. Now, you can see here what we're looking at is essentially a kid's toy. It's RC Super Mario Kart. And I'm going to toggle on the white LEDs. Again, this helps when we're talking about capturing colors. I'm going to use color scanning. I'm still using marker tracking because in this case, I want to use the mat because that's going to help me capture accurate data. I'm going to use the standard accuracy marker tracking general object. I'm going to press the button on the back of the scanner and just begin scanning. I'm going to just work my way around manually. I'm not going to capture this entire thing, but we are going to start to see that areas that are black, like the tires, the steering wheel, it's not going to capture those. And this is just a general thing with scanners. If we lose tracking, we can pull the scanner away a little bit, go back until it can find the data. And then as soon as we see the green preview, that's going to be able to sort of help us get back to capturing data in the correct location. So once again, I'm not going to do everything, but I will work my way around. Let's try to get some of the yellow. And I'm going to hang out here for a second, maybe try to get the rest of Mario's head. And then we'll come up over the top. We'll need to pull away a little bit so I do have enough markers in there. And see if we can't capture the rest of his hat. Just move over like that. All right, so go ahead and pause that and take a look. We're not going to go through the process of cleaning this up and processing it, but you can see that each point carries color data with it. So we can see the eyes, we can see anything that's red or skin tone, getting a little bit of the tires, but the steering wheel is definitely not there. The mufflers are kind of there, but not really. And I didn't do any prep to this. It's just the way that it is, but it is capturing pretty well. Once we're done with this, we can go through all the same steps. We can use the fusion process, depending on how you captured it, depending on what your requirements are in terms of the number of polygons you want in the mesh. You can determine how you want to fuse the points together. You can determine whether or not you want to remove a lot of the extra noise that was in the scan and just simply move down the line, just like we did with the fender and just like we did with the bar clamp. All right, so fusing is complete. And I'm just going to go ahead and mesh. I'm not going to clean anything else up. Again, grid size, we don't want to go all the way to 6 because any noise that we have in the scan is just going to come through. All right, and now we have a colored mesh. So you can see we got a little bit of the mufflers. We've got Mario. We've got his boots. Even got the seam on the side of his pants. So we got some pretty good detail out of this, and I didn't spend a lot of time scanning. I didn't really do any prep to the mesh after the fusion. I didn't clean anything up. So this is a pretty good result. We could certainly spend some more time. If it did have scanning spray on it, we would get a much better result, but we wouldn't capture color data. So the scanner does really well with objects that are this size. So this is probably 10 inches long. There's a drastic difference between the size of the bar clamp. And I'll go ahead and I'll just put the bar clamp sort of on it so you can kind of see the size discrepancy here. So the bar clamp is the part that we want to reverse engineer. It's quite a bit smaller. It's about the size of Mario's head. And that's the data that we wanted, which is quite a bit smaller than this toy. So keep in mind, there is going to be a usable range. If you want to reverse engineer smaller parts, then the Revopoint, the Mini, is probably the best scanner in terms of what Revopoint has to offer. The Pop3 is going to be kind of in that middle range where you're looking at larger objects. And then the Inspire is going to be kind of in the same range as the Pop3 for the size of the objects. However, it's going to be less expensive. It's going to kind of work in that same area, but you will have some reduced quality. You will have reduced capture and all that kind of stuff. So now that we've seen a couple of examples on the scanning side, let's go ahead and bring some of this data into Fusion, and we can kind of see what it looks like in CAD and talk about some of the things that we need to do to reverse engineer. All right, so in Fusion 360, we're going to go to our mesh tools and select Insert Mesh. We're going to pick the files on the computer, and I'm going to start with the KTM clamp, and we're going to go ahead and select that. Now, one of the main issues that you're going to run into with this process is that there's no alignment to a coordinate system. So when you open it, it's going to be based on the orientation and how you scanned it. So when we look at this, this is essentially how the scanner was looking at the object. With that in mind, you can do a little work to plan your first scan based on the orientation you want it to come into the CAD program, in this case, Fusion 360. But if you want it aligned to some specific coordinate system, you'd have to go into something like GOM Inspect. The free version will let you do that. You can play around with aligning it manually. So for example, we can rotate this a bit, go to a top view, kind of rotate it that way. I'm going to say OK, go to my bodies, and go to Move Copy again, and rotate to the side. And this is by no means ideal. So I think I want to go to maybe 34 degrees. Maybe down to 33. And what I'm looking for here is that both of these points are touching. I'm going to say OK. Go to a different view here. Move it one more time. Say OK. And now we're looking pretty good, but we need to rotate it here. And once more. Say okay. So once again, not ideal, and you can see the orientation relative to our coordinate system's not right. So once we have it in line with X, Y, and Z, then we can go through the process of getting it to be in somewhat of a correct orientation. So now we can go 90 degrees. That's going to be my right view. That's going to be my front view, and that'll be fine. From here, I'm not going to go through the process of reverse engineering this because we've done this exact same part before. So if you take a look at the link on the screen, you can go through that process with different scan data, albeit the same exact process of using mesh section sketches. Now, with that in mind, we can take a look at the scan. And once again, this is where one of the scans sort of ended and the other scan picked up. And that's why we've got a lot of noise or bumps in those corners. You can take this in Fusion and remesh it. So if you want to do a remesh in Fusion, you can, to try to clean up the mesh elements. You can play around with removing those corners if you want. But again, whenever you're doing something like this, the critical data is likely going to come from manual measurements. You're not going to be going through the process of doing this with the measurements off of the scan data. It's going to come from calipers and it's going to come from measuring the features. So with that said, I think that this result is actually pretty decent. We can still see some of the details that we would want to capture. Other details that are critical, things like the hole locations, that would all come from measuring the part. And I think that this is a pretty good result. Next, let's take a look at bringing in the Starion fender. So I'm going to go to Insert Mesh. Once again, I'm going to find that data. This is going to be Starion canard. And once again, the orientation of this is going to be based on how it was scanned. Now, this was scanned in nearly the correct orientation, so all we really need to do is rotate it a little bit. I'm going to go to numerical inputs, and 15 degrees is going to be too much, and 10 is not enough. So I'm going to try 12 degrees, and that looks pretty good. And then I'm going to go to a front view, and it's pretty much that angle on the car. So I think that's actually pretty good as well. Now, I'm going to hide the edges and take a look at the scan. Once again, that looks fine. There's not really anything wrong with that. When we're talking about using something like the Revopoint Inspire, that scanner is really not meant for high precision reverse engineering. It is possible, and we can likely get the details that we need off of that scanner. You need to find where that point is. And then we can begin working with this data. So let's go ahead and move that out a little bit. And so you can see we can begin building this, and we can use tools like pull, and we can pull these vertices directly down to the underlying mesh if we want. And we can rebuild that surface to be somewhat close to the scan data and use that to start building our parts. So again, I've done this process many times. I'm not going to go through it because we just did it recently off of the same section of the car using surface tools and freeform modeling tools. But mainly what I wanted to look at was the scan data off the Revopoint Inspire. Wanted to see what that looked like in Fusion for both the KTM bar clamp as well as part of the Starion fender. So that brings us to the end of this video, which is coming up on about an hour, which is kind of crazy. But the end of this, we really need to figure out, is this scanner worth your money? Should you buy this scanner for what you need to do? And I think it really comes back down to having a specific intent for what you want to do. Now, if you need a general purpose scanner, if you're not really sure what you're going to be scanning, I think that the Inspire is going to come in at a pretty low price point. It's going to be hard to beat in terms of the amount of money you'd have to spend getting into scanning. RevoScan is free. And again, you don't really need a high horsepower computer to be able to run this. So that is a big plus in my mind, because if you're a hobby user for Fusion 360, you're on a free license. RevoScan is free, And the scanner itself, I'm going to guess it's somewhere under $500. I'm not really sure until we see what the Kickstarter launches, but I think that's a really good value to get into being able to do this kind of thing. You could spend $500 on a scanner, $500 on a 3D printer, and be on your way to reverse engineering and designing parts off of scanned data. Now, if you spend a little bit more money, or if you have a specific task in mind, if you're always looking at reverse engineering small parts, then probably this isn't the scanner for you. Probably going to the Mini series, which is likely going to be a little bit more expensive, is the best thing. If you're looking for larger scans, if you're looking to use, interiors of cars or things like that, then looking at the Range series of scanners, that is probably going to be better than something like this Inspire. It's really looking like, and again, without all the information out there, it's really looking like this is an entry-level scanner. This is where you would want to start 3D scanning without investing a ton of money. So with all that said, if you have any questions on anything you've seen so far, please let me know. If you want to see any more with this scanner, if you want us to go through the process of scanning something and working through reverse engineering, something that we haven't already done, a part that we haven't already scanned, then please let me know that. And if you want to see other scanners like this, if you want to see the Mini, or if you want to see the Range, or if there's something else that you want to see, let me know that as well. So if you have any questions, please leave the comments below. And as always, thanks for watching. We'll see you in the next one.